Okay, thank you very much. So this is on Pluribus, our superhuman AI for multiplayer poker. This is joint work with Professor Tomas Sandholm at Carnegie Mellon. So for starters, this talk is about imperfect information games. Most AI research when it comes to games is focused on perfect information games like chess or Go. But most real-world strategic interactions involve some amount of hidden information, such as negotiations, financial markets, or even navigating traffic at a busy intersection. And when it comes to these games, a primary benchmark and challenge problem is poker, and in particular, a variant of poker called no-limit Texas Hold'em. So this has been a longstanding challenge problem in AI and game theory. In fact, some of the first papers written by John Nash on Nash equilibria talked about poker. No-limit Texas Hold'em in particular is a massive version of poker. The two-player version has 10 to the 161 decision points. And it's also by far the most popular form of poker. So for example, it's featured in popular movies about poker like Casino Royale or Rounders. So here we have a picture of James Bond playing No-limit Texas Hold'em in Casino Royale. And it's also used, for example, to determine the winner of the World Series of Poker main events. Now, in 2017, we created an AI called Pluribus that was able to beat 4 of the world's best heads-up no-limit Texas Hold'em poker pros. This is two-player no-limit Texas Hold'em. So we played 120,000 hands over the course of 20 days in 2017, and the bot won by a decisive margin. And what's interesting about Pluribus is that it was trained entirely from self-play. There was no human data that went into the bot. Now, that said, the training was fairly expensive. It used about 3 million core hours, which would cost about $100,000 in cloud computing credits, and to run it in real time used about 1,200 CPU cores. And this was considered a major achievement at the time, but when we were giving talks about this work, the number one question we got was, well, what about more than 2 players? I mean, if you've ever played poker, you know that it's traditional to play poker with more than 2 players. And there's a lot of challenges going from 2-player to multiplayer poker, and people raise these questions. So first of all, one of the major challenges is the larger size. So as you add more players, there are exponentially more sequences of actions that can occur. And so just in terms of game size, it grows exponentially. And so for example, the search techniques that we used in Pluribus, if we were to use them in 6-player poker, would have required about 100,000 times as much compute. There are also game theoretic challenges when you go from 2-player zero-sum to more than 2 players. So for example, regret minimization, which is what we use to compute the strategy for 2-player poker, regret minimization no longer converges to a Nash equilibrium. And beyond that, even if you could compute a Nash equilibrium, it's unclear if you would want to play it. It's not clear if any equilibrium, in fact, is the right goal in a game like 6-player poker. So, but nevertheless, in 2019, we created Pluribus, which played against 15 top professionals in 6-player no-limit Texas Hold'em. So we had the bot plus 5 humans at the table. We played 10,000 hands over the course of 12 days, and we used variance reduction techniques to decrease the luck factor so we could determine the strength of the bot with statistical significance. There was $50,000 divided among the pros to incentivize them to play their best, and the bot won with statistical significance. And what's interesting about Pluribus is that despite the massive increase in the size of the game, Pluribus was much cheaper to train and to run than Pluribus. In fact, to train Pluribus on a cloud service like AWS would cost less than $150. And running it in real time used only a 28-core CPU, and there were no GPUs that were needed. And so I think there are some really interesting things that can be drawn from this. So first of all, even though there are major theoretical challenges that come up when going from 2-player to more than 2 players, we found that the regret minimization techniques that were used in 2-player were actually quite effective in 6-player no-limit Texas Hold'em. And I think this suggests that even though there are theoretical challenges in going from 2-player to more than 2 players, even though regret minimization does have theoretical guarantee, it converges to a coarse correlated equilibrium outside of 2-player zero-sum games, that isn't necessarily a useful theoretical result in 6-player no-limit Texas Hold'em. But nevertheless, we see that these regret minimization techniques can compute effective strategies that defeat professional players. The other interesting result is that even though the game has increased in size, the cost to train and to run this bot has decreased by orders of magnitude. And the reason we were able to achieve this is because of depth limited search, which I'll talk about later in this talk. Okay, so now I want to give an overview of what Pluribus looks like. The idea behind Pluribus is that we have this massive game, which is simply way too large to solve in its entirety. And so instead what we do is come up with an abstraction of the game, a simpler version of the game, a much smaller version of the game that tries to retain as much as possible the strategic elements of it, of the full game. So this abstraction is particularly detailed in the early parts of the game, but then just approximates how to play in the later parts. And then when we're actually playing, when we encounter one of these later parts of the game where we don't have a very high quality, very fine-grained strategy, we will in real time do depth limited search, which will compute a better strategy in real time. This is like with chess AIs, they don't act instantaneously. They take 10 or 15 seconds to decide what their next move should be. This is exactly what Pluribus is doing, but in a more complicated way. Now, this search only extends some depth to some depth limit. Beyond that, it again uses a coarse-grained approximation of what the equilibrium will look like. And this process repeats as we go down the game tree. When we encounter another subgame, we again do search for depth limit. So the first step of this process is shrinking the massive game down to a reasonable size. And to do this, we used card abstraction and action abstraction. And the idea here is that there might be billions of different poker hands in a game like No Limit Texas Hold'em, but we can cluster similar hands together and treat them identically. And then we only have to come up with a single strategy for all of these similar situations instead of a unique strategy for each of those situations. So for example, in this situation, there might be these 5 cards on the board, and there might be these 2 different poker hands, and we can group them together and treat them identically because they are strategically similar. Now that said, card abstraction, there are subtle differences between different poker hands, and so card abstraction has its limits. It doesn't fully capture what the equilibrium should look like, but it does a pretty good job of approximating it. And so using this card abstraction, we reduced the number of possible hands. For example, in the last round of poker, there are over 1 billion possible hands. We reduced that number to just 200 in the blueprint strategy, the strategy that does not use search. So once we have this shrinked abstract game, we run something called Monte Carlo Counterfactual Regret Minimization. This is a Monte Carlo version of regret minimization, which can be applied to sequential games to find an approximate equilibrium. So the idea of this is it's an iterative algorithm where the bot plays against itself. It starts completely playing a uniform random strategy, and over time it gradually improves until it approximates an equilibrium. So I'm going to step through a couple iterations of this algorithm just so you can see what it looks like. The algorithm starts by picking up 1 player, and it will update regret only for that player. And actions are picked in proportion to the amount of positive regret on the action. So we have this regret value on every action in the game, and we will update this value over time. Now the regrets all start at 0, so we pick an action uniform random because all the actions have equal regret. So player 1 might pick to go left. When we encounter a player 2 node, we again pick an action proportional to the amount of positive regret, which means that we pick uniform random on the first iteration. So we might go left. Player 1 again picks uniform random and maybe receives a payoff of $50. So now player 1 is going to review every decision that they could have made, every alternative decision that they could have made, and see what the payoff would have been for those other hypothetical situations. So for example, player 1 might see if they had gone right instead, they would have received a reward of $100. And so the regret for that action increases by the difference between what they could have received versus what they actually received. So the regret will increase by 50. And we are able to obtain these hypothetical rewards because we are in a self-play setting. Player 1 is playing against a copy of itself, so it knows that if it had gone right, then player 2 would have done this, and player 3 would have done this, and eventually a reward of $100 would have been received. And by the way, I would argue that this is actually quite similar to how humans learn to play a game like poker. If you've ever played a game like poker, it's really common for a person to ask, if I had raised, would you have called me? And so this is exactly what the bot is doing. The bot is asking, if it had done this other action instead, what would my opponents have done? And it's learning from that information. So player 1 will then pass up the reward that was actually received. We're going to skip the player 2 node because we're only updating regrets for player 1 in this iteration. And player 1 will again see what they could have received for choosing the other actions instead. So if they had gone right, maybe they would have encountered another player 1 node. In this situation, they would have chosen to go left, and they would have received a reward of minus $500. If they had gone right instead, they could have received a reward of 100. And so the regret for that right action increases to 600. Since they would have chosen the reward leading to minus 500 if they had gone right, the hypothetical reward for the top node is minus 500. You can't cheat and see what the rewards are before you choose your action. So the regret for that right action becomes minus 550. And in the future, after this iteration is complete, we'll do the same thing for player 2. Then we'll cycle through all the players, and when we get back to player 1, actions that have higher regret will be played with higher probability. Now, in Pluribus, we used an improvement of pruning, which, there might be situations, there might be actions in this game that are consistently giving a negative reward. So maybe that top right action at the very beginning is consistently giving a reward of minus $500. Well, it's pretty clear in that case that we don't want to waste a lot of time exploring that branch of the game tree because we shouldn't be choosing that action anyway. And so by using pruning, we can explore those extremely negative regret actions with lower probability and focus more of our efforts on the more interesting, more useful parts of the game tree. And in practice, this sped up Monte Carlo CFR by about a factor of 3. Now, CFR is just like what I described, except it does not involve random actions. The theoretical convergence bound, you take the expectation over all of the actions. So the theoretical convergence bound for CFR is order IA over t to the 0.5, where I is the number of decision points, A is the number of actions of those decision points, and T is the number of iterations that you've played. So as T goes to infinity, you will ultimately converge to a Nash equilibrium. Now that said, in practice, state-of-the-art variants converge much faster in practice. State-of-the-art variants converge in practice at rate of 1 over t to the 1.5. Okay, so using CFR, Monte Carlo CFR, we can compute an equilibrium. And in two-player zero-sum games, this will converge to a Nash equilibrium or a min-max equilibrium. Outside of two-player zero-sum games, it's only guaranteed to converge to a coarse correlated equilibrium, though there is recent work suggesting it might converge to an extensive form coarse correlated equilibrium, which is a slightly stronger solution concept. Okay, so we have hopefully a good approximation of what a good strategy should look like. But because we're doing this Monte Carlo CFR on an abstract version of the game, it's not giving us an exact equilibrium, even if the equilibrium is something that we want to compute. And so during when we're actually playing the game in real time, we will search for an improved strategy that will give us a finer grained approximation of what the equilibrium might look like. So the first thing I want to argue is that real-time search is extremely important. And in fact, if you look at pretty much all of the previous AI breakthroughs in games, they have all used search in some form. So for example, here is a plot showing different versions of AlphaGo. The highest bar is AlphaGo 0. On the y-axis, we have ELO rating, which is a measure of performance. And we can see that AlphaGo 0 has an ELO rating of over 5,000, which is clearly superhuman. Top human performance is around 3,600 ELO. But if you take out the Monte Carlo tree search component from AlphaGo 0, that is just the part of Monte Carlo tree search that is used at test time, the ELO rating drops to around 3,000. So that's below superhuman performance. So what this shows is that deep reinforcement learning alone is not enough to beat top humans in Go. You have to use tree search as well, Monte Carlo tree search. And like I said, this has been true for pretty much all of the previous AI breakthroughs in games. Backgammon used 2-ply search, Deep Blue used alpha beta pruning, and one of the key reasons why we were able to beat top humans both in the 2-player version of poker and the 6-player version of poker is because we figured out how to use search in imperfect information games, in adversarial imperfect information games. Now, search, unfortunately, is not easy to use in imperfect information games. It's actually much more complicated than perfect information games, which is why it was not used for a very long time. So I'll give a demonstration of this difficulty. In perfect information games and single agent settings, if you want to do search, it looks something like this. You take some action, your opponent takes some action, you're in some subgame, but this remaining subgame is too large to solve to the end of the game. And so instead, you just search over a limited depth. And at the end of this depth, you reach a leaf node and you estimate the value of that leaf node as the value of both players playing perfectly from that point forward. And if this estimate is perfect, then depth limited search will return an optimal strategy for the next few moves, and you can play according to that. But in imperfect information games, this is not true. And I'll give a simple demonstration showing this. So here is a version of rock, paper, scissors called rock, paper, scissors plus. It's just like rock, paper, scissors, except if either player chooses scissors, then the winner receives 2 points and the loser loses 2 points. And we're doing this just to break the symmetry of the game. So now in this version of rock, paper, scissors, the equilibrium is to choose rock and paper with 40% probability and scissors with 20% probability. And I'm showing a sequential version of this game where player 1 acts first and then player 2 acts without observing what player 1 did, which is why there are the dotted lines between the player 2 nodes. Okay, so let's say we were to play a depth limited version. Let's say we were to do search as player 1 in this game, and we do it in the same style as perfect information games. So we as player 1 look 1 move ahead, and then we stop there and substitute the value of both players playing perfectly from that point forward. So this is what that subgame would look like. And you can see if we were to solve this depth limited subgame, there is not enough information for us to arrive at the equilibrium of choosing rock and paper 40% probability and scissors with 20% probability. We might arrive at always throwing rock, we might arrive at 1/3, 1/3, 1/3, but there is not enough information to arrive at the equilibrium. And the reason for this is because we are assuming that player 2 is going to play the equilibrium strategy no matter what we choose as player 1. And indeed, if that were true, if player 2 were to always play rock and paper 40% probability, scissors 20% probability, then we could always throw rock and receive an expected value of 0. But in practice, that's not what would actually happen. If we were to, for example, throw rock with 80% probability, then player 2 would shift to a different strategy of always throwing paper. And the value of rock would drop to become -1. And so this idea of assigning unique values to leaf nodes works in perfect information games, but it doesn't work when you go to imperfect information games. So what we do instead in Pluribus is we explicitly acknowledge that players might deviate to different strategies other than the equilibrium. And so when we're doing depth limited search, when we reach a leaf node, we give each player a choice between multiple different strategies that they could play for the remainder of the game. So on the left here, this is an example of what a subgame might look like. We arrive at some root node where we cannot distinguish exactly what node we are in. We do a depth limited search, and there are a bunch of leaf nodes at the end of this subgame. Now, at those leaf nodes, we allow each player to choose between multiple different strategies. One of those strategies is indeed to play the Nash equilibrium, but it might also include strategies like call more often than the equilibrium or raise more often than the equilibrium. And by giving each player the choice of these different strategies, we learn to be robust to the different strategies that the players might shift to if we were to not play an equilibrium. And we find in small games that this does in fact reduce exploitability. So it gets us closer to an equilibrium in these subgames. So for example, on this plot, we have exploitability on the y-axis, which is just how far away we are from a Nash equilibrium. So lower numbers get us closer to a Nash equilibrium. And the x-axis is the number of different strategies that players can choose at the leaf nodes. And we see that the exploitability drops off quite dramatically as we add more and more strategies for the players. And of course, in the limit where we allow players to choose any strategy they want for the remainder of the game, exploitability is provably goes down to 0. And I should say this exploitability goes down to 0 specifically for 2-player zero-sum games. Again, when you go beyond 2-player zero-sum, a lot of the theoretical guarantees are lost. Okay, so there's a question of what happens now. I think it's safe to say that poker is exhausted as a benchmark. You could, of course, go beyond 6 players to something like 9 players. That said, the techniques that we have work quite well in those settings. So for example, 6-player cost $150 to compute. If you were to go to 9 players, it would cost more, but it would not be astronomical. And so the reason why we chose 6 players, in fact, is because 6 players is the most common version of no-limit Texas Hold'em. That said, I think the techniques that are used in different games, so for example, the techniques that are used in Go are quite different from the techniques that are used in poker. And a promising line of research is finding more general techniques. Can we have a single algorithm that plays games like poker and Go? Of course, another promising path, which I think is the most difficult challenge, is going beyond zero-sum games. So even though we've addressed 6-player poker, 6-player poker is still a very adversarial game. There are very limited opportunities for collaboration, for negotiation, and cooperation. But the real world is much more complicated than that. The real world is not zero sum. And AI is still struggling with this challenge when we go beyond zero sum games. So I will stop there and I will take questions. Thank you very much.